What is happening YouTube, and welcome back to the ASX Portfolio channel. My name's Jonathan. So today we're going to be talking about the difference between simple and log returns. We're also going to talk about, is financial data normally distributed or not? So for those of you who don't want to stick around for the coding, to find out the answer with why we would want to use normal distribution and what's the difference between log and simple returns, let's look at this here. So if we want to model returns using the normal distribution, because it's very easy to do this, it's very easy to model returns and simulate this normal distribution process. Can you use simple returns for this? Well, no, because the product of normally distributed variables is not normally distributed. But log returns the sum of normally distributed variables, or normally distributed produced variables, as we would be simulating returns from the normal distribution process. This would follow a normal distribution. So why would simple returns lead to the product, and why would log returns lead to the sum of these normal distributed variables? Well, for that you'd have to keep watching. So for those who want to keep watching, let's jump in. So first off, let's import all the dependencies. I haven't typed them out here because we've been doing that for the last 2 episodes as a part of this series. So let's just go ahead and type them up now. Date, time, pandas, NumPy we're adding, which might be different. PyLab, Seaborn, and SciPy stats. They're the different ones. Whereas the last 2 episodes, we have been using Pandas Data Reader and Plotly offline. Don't forget to initialize the notebook and call Pandas Data Frame Backend as Plotly. So, moving on. Step 2, you got to get the stock market data. Choose your data range. Here we've chosen the end, which is the latest financial data point that we have available to us, and the start date 2018. So, of course, here we've got CBA as our use case for this financial data, and this is what we'll be testing. So I've just printed out the data frame there. So let's get stuck into what is simple returns and what are log returns. So simple returns, as you can see from the math here, the 1 period simple return is simply the difference from one day's price to the next divided by the day before. So the difference between the price today and the price yesterday minus 1. Also represented in the 1 plus return equals the difference between the prices form. So let's calculate the simple returns. So simple returns are going to be equal to that df.close.percent change. And you can see there we've got the NAN because we're using 1 day's worth of information to even compute the simple change. So we can drop all those NANs and we just remove the first day of information. So we have the different simple returns, daily simple returns. If we wanted to compute the multi-period returns, so across multiple days, what is the simple returns? This is where the product comes from. We'd have to multiply the different returns for each day to get the sum of those returns over that period. So it'd be 1 plus this value times 1 plus this value times 1 plus this value. And you can look at the maths here and kind of work it out for yourselves why this is the case. Now, that isn't really a handy property to have when you're dealing with financial data. We'd like to be able to just take the mean over these values and say, hey, that is the percentage across this entire time period. Let's try and calculate stuff from it. So I'll show you what I mean why it's not very handy. If we plot a graph of the close prices, so df.close.plot. So if this automatically goes all the way out to the other side of the page, I'm not going to like that for this episode. So let's go update layout. I'll teach you a trick here. We're going to say auto size, and we're going to call that false. Then we'll call the width 500 and the height 300. Cool, so we've made it a lot smaller, easier to see on the same page. So now that we can see the prices have gone from about 80 to 90, let's get those exact numbers. So we're going to print the first data point in this price trace, and that'll be df.close, the first point, and then we're going to get the last point. So last, and we're going to access the last data point by indexing by -1. So you can see here we started at $80.22, and then it's gone to $89.59, or what have you. So let's try and use this simple, let's see the limitations of simple returns by trying to use this to calculate the last price from the first state using this information. So simple returns mean the average across all those days is this. And let's try and, let's use a bit of logic. We'd like to be able to take the close price, and we'd like to be able to compute the simple returns every day. So take the mean of those simple returns, and we're going to have that to the power of the amount of days. So the amount of days in this time frame, I want to take that mean return, multiply this mean return every single day from the very beginning to see if I get the end stock price. And of course I don't. And I don't because of the math that we saw above. We need to actually take the product of all these 1+ daily returns. So this is kind of annoying. I can't use my simple returns mean. It's not a very descriptive or useful statistic for me to be able to work out. What I'd have to do if I wanted to compute that accurately is take the products. So we're going to use NumPy product over list comprehension, and we're going to take 1 plus RT for RT in simple returns. So as you can see here, I've been able to work out the exact last close price given the entire simple return price series. Now it's not very easy, it's not intuitive. I can't point to this simple returns mean, and it doesn't describe a lot of stuff by itself. So whereas the log returns has a really nice property that when you add these daily returns up, these incremental returns over time, it is descriptive of your data set, and you can use it in a very useful way. So an additive property is really nice when it comes to log returns. So to put that in perspective, to see those differences there, let's compute the log returns now. So you can see to compute the log returns, we just need to take the df closes. What we need to do is take the np log, and we're going to transform the closes. We're going to divide it by the close from the previous day. And the way we do that, we call the close price, and then we go .shift, and we're going to shift by 1 period. So this is what you need. You just go log returns to print it out. And again, you can see that we've got the NA because we've used 1 price day's information. So we're going to just drop NAs to remove that day. So now that we've got the log returns, let's use it, and so you can see what I've been talking about. So to compute the mean return, we can see that that's very different to the simple return. Doesn't mean we can't use it in a more useful way now. So we're going to now take that close price from the first time in our series back in 2018, and we're going to take the exponent of the average mean multiplied by, again, the length of this data frame, the number of days. And you'll see that we can calculate accurately what the price is at the end of the time series based off the mean. It suddenly gives us a lot of useful value, this summary statistic. So that's a nice property to have. But again, I want to iterate, that's not the only reason. If you want to model returns using the normal distribution, because it is so easy to simulate a random variable from the normal distribution, then you cannot use the simple returns, because the product of the normal distributed variables do not result in a normal distribution Okay, so if you take the product of all these different normal variables, you will not end up with a normal distribution. Whereas if you take the sum of these normally distributed variables or assumed normally distributed variables, then you will end up with a normal distribution. And that's really nice. That's a nice property to have. A lot of formulas and assumptions and theorems out there assume normal distribution. So handy to have. Also a handy property is that the log distribution bounds our stock price at 0, which is a nice property to have again, because this is stock prices in reality stop at 0, and so does this log distribution. So let's take a look at the log return histogram. So we just call log returns dot plot, and we call kind equals hist. So I'm going to take that update layout part from up there again, and we'll just plot that. So it's kind of interesting to see it all centered around 0% here. Looks a little bit normally distributed here, but you can see some really fat tails. We can see some occurrences that are on the left-hand side and on the right-hand side. So is this log returns normally distributed? Are the percentage change of log returns normally distributed? And is that a good assumption for financial data? Well, let's take this worst case and this best case and see how many standard deviations and what the probability of those occurrences would be if we assumed that it was normally distributed. So first thing we've got to do, we've got to get those log returns. Log return, what did I call it? Log returns to list. Whoop. And I'll call this the log returns sorted. So to not make me a liar, we'll go .sort on that. And we'll just print that out to show you what we're doing there. So we've now just got the sorted returns, and I've got the lowest case at the top and the highest case at the bottom. So if I index by 0, I'll get the worst case, and if I index by -1, I'll get the best case. So let's just call that worst and best. Worst and best. Excellent. So now this is a percentage. I want to get that in terms of standard deviations away from the mean. So we have to normalize the data. So standard deviation worst, we'll call it, and then standard deviation best. And we're going to take the worst minus the mean of the log returns, and we're going to divide through by the standard deviations. And that will normalize these, that worst case scenario and also the best case scenario. Cool. So let's print this out in a very useful way. Let's say print, so I want to know the standard deviation. And remember, this is under the normal, normal distribution case. The worst is going to be, and the best is going to be here. So just using this notation so I can get a certain number of floats. So worst and best. So the standard deviations in the worst case are -6.5 and the best is 7.6. So that's a huge standard deviations, considering that, what is it in the normal distribution, 99.7% of the data or something is within 3 standard deviations away from the mean. So massive standard deviation moves. Let's see what those probabilities correspond to. So let's go probability of worst and probability of best, and the way we're going to do that is we're going to call stats.norm. So the normal distribution centered around 0 and 1. And the reason we're doing that, we've already normalized the worst and best cases. We just need to take the normal distribution, standard normal distribution around 0 with standard deviation of 1, and then call the PDF to see the likelihood of having an event at that case. Hopefully that makes sense. So the probability of the worst is 0 and the best is 0. Let's increase these floats. So this seems like it's to a factor of 10. And this probability is to a factor of 10 to the 13. So it is incredibly small probabilities that under the normal distribution you would ever see these financial moves. So that's already screaming, wow, financial data is not normally distributed. How do we actually go about proving this? Okay, so there are a few ways. We can do it visually and we can do it numerically. Numerically, we're going to be doing hypothesis testing, so inference, statistical inference, or through the visual method, I think is quite powerful as well, and it's probably best used in the first case. So let's go through the visual aspect. We've already talked about one, and that is doing a histogram, and you could plot the normal distribution as a line on this and be able to compare. That's fairly good. Another one that I really like is the Quantile-Quantile Plots. So let's talk about that. So it's the stats module again. So stats module, and you just go prob plot log returns, which is still our df there. Now the distribution we want to compare it to is norm. Now a great thing about the Quantile-Quantile Plots is that you could compute the theoretical quantiles with actual quantiles for any distribution we want, which is really nice. Plot equals pylab. And we'll just print QQ plot. So QQ plot, here you go. You can see that this red line represents the normal distribution and the blue dots are the quantiles of our actual distribution for the log returns data. You can see that they pretty well map each other out in this middle section. But as you get out to the tails, we've got very thick tails for financial data in general. But here in CBA, we can see it quite well. So it starts deviating away from this normal distribution line. And that's what we saw here, right? We saw that the probabilities were so small for these events actually occurring. But in fact, in financial data, they do occur. So this is a great way to see, is it normally distributed? Well, probably not best if you were representing it from the tails. But if you are only dealing with this data in the middle, a normal distribution is, looks like it could be a pretty good way to go. But if you want to represent the whole financial population, or represent CBA returns as a whole, then maybe normal distribution, not the way to go. Another way you can look at this data is through box plots. So box plots, you have the quartiles, you look at the min and max, it's pretty cool. Very easy with Plotly and pandas. So plot, we're just going to say kind equals box this time, and we'll grab that update layout. Bam. So you can see here that we've got dot points way further than this upper fence and lower fence that the box plot's got for us. So outliers, so to speak. And really what that's saying is we've got very heavy tails to either side. So for up moves and down moves of the stock price. So, that's indicating there that maybe we don't have a normally distributed data. So quantitatively, why would you want to do the hypothesis test if we can just look at this and go, oh, that's not normally distributed from a QQ plot or box plot? Well, it is very objective. Having a numerical answer and a statistical framework to be able to say this is normally distributed and this is not. The most popular way that comes to mind is this test right here, the KS test, the Kolmogorov Smirnov test. I am terrible at pronouncing that, but the KS test. So this computes the distances between the empirical distribution, so our actual distribution that we're calculating, and the theoretical distribution that we want to compare it to. That defines the test statistic, and then it's essentially just a set of the distances between them. So the test statistic of the KS test compares this distribution, and the null hypothesis is essentially true if it follows this distribution. But if the observed data perfectly follows a normal distribution, the value of the KS statistic will be 0. So the p-value, the probability, is going to be used to decide whether the difference is large enough to reject this null hypothesis. So the advantage of having this approach is that we can use it for any distribution, not only the normal distribution, which is great to have. So we're going to use the stats module for this. So first thing, let's call it the KS statistic and the p-value. So we're going to call the stats library KS test, and we'll go log returns, we'll compare it to the normal distribution, and we're going to say that's it. So we'll print out these values. Great, and we're just gonna do the threshold thing now. So if the p-value is greater than 0.05, our confidence interval, whatever level you want to set, the 5th percentile, the 10th percentile, so be it. You are who you are. The probability will be probably Gaussian. So it's going to be normally distributed to this confidence interval. You can be stricter with that confidence interval, obviously. Else, if we don't take that, then the probability is not Gaussian. So now that we've run the KS test, we're going to talk about the p-value. So if the p-value was greater than the 0.05, it's probably Gaussian. Else, we have to reject the null hypothesis that the two distributions are the same and they're probably not Gaussian. So in our case, the difference between those two distributions was quite large. It was not 0, and the p-value was very low under that threshold value that we set. So it's probably not Gaussian. So now moving on to the Shapiro Wilk test, if we copy and paste that down there, the Shapiro Wilk test is the most powerful test when we're comparing to the normal distribution. The reason is it's specifically being developed to test the normal distribution and the normal distribution alone. So I guess here it's very good that the KS test is general for different distributions, but here very specific, and it's a great test. So we're going to go Shapiro Wilkinson SW stat, put that down there. To call the statistic, we just go Shapiro and get rid of the norm now, because we don't need to tell it which distribution to compare to. So we'll run that, and again, in a similar fashion, we reject the null hypothesis that they're the same because we've got a big distance between the two distributions, empirical and theoretical, and the p-value is extremely small and doesn't go above that threshold. So it is probably not Gaussian. Now the interesting thing is, if we actually tighten this data range, so we don't have large movements, so from 2021, just 3 months worth of data, 4 months worth of data, I know we haven't had any huge moves. We can see that the Shapiro Wilk test actually has a Gaussian distribution. And if you look up here, the probability plot, it's extremely close. We don't have any of those fat tails now. So within this time horizon that we're looking at in the financial data, the data is normally distributed for the last 4 months. So, it's very interesting, but of course we're talking generally financial data over a long period of time experiences these large moves, and those large moves, when considering and trying to capture those moves in the normal distribution, it's not the best tool. So we're going to talk about what those tools are in later videos, but normally distributed variables and the assumption around returns, it's very easy to be able to generate normal variables, normally distributed variables, and that's why it's used so heavily in models. Also, the maths is extremely, it's significant in the reduction in complexity when making that assumption for a lot of the theoretical models. One being option pricing and the Black-Scholes for European options. So thank you very much for listening. If you liked the video, please give it a like and subscribe to the channel for more. See you next time.